Okay, we're going to take a look at the derivation and the concept behind trying to find the surface area of revolution. So we have this curve, y equals f of x, that we like to revolve around some axis. It could be the x-axis, it could be the y-axis. Technically, it could be some other vertical or horizontal line. But for us, we'll stick to just the x or y-axis. So I take a curve, revolve it, and I'll have a surface. And I would like to find the area of that surface. So here's what we're going to do. We're going to chop that interval from a to b up into subintervals. And so here's a typical subinterval. Call it the ith subinterval. And we want to take a look at the band that's created by that. We connect the 2 points here. Call one x sub k, or I, sorry, x sub I minus 1, and the other x sub I. And so we get x sub I minus 1 for here, and then x sub I for here. We plug them in, we get a point. P sub I minus 1 is the y value, P sub I is the other y value. Okay, so P sub I minus 1 is f of x sub I minus 1. Okay, alright, great. What this does is we have a connection between these 2 points. We take the point here and connect it to the point here. And we have this connection here. And we're going to then take this band that's created and we're going to unroll it. And so we'll have basically a rectangle where the height will be the circumference. We'll have 2 pi r as the one dimension, and then the height is the other dimension. Okay, and that would be the area of the band can then be found by taking them and multiplying 2 pi r h. But we need an r and we need an h. And so here's what we're going to do. We're going to take the sort of, we have a left and a right. We're going to take an average height. And then for the length, or this is what we call the height, for the height we're going to take the distance between these 2 points. Call it d. Distance formula, right? We take subtract the x's, square, subtract the y's, square, take a square root, and then that would be our distance. And so that's what we're going to have for the distance between these 2 points. So the radius then will be the average height. So we take, basically this could be written as P sub I minus 1 and P sub I, but we call it y here. And so this symbol here represents this distance, but we can use what we did from the arc length section and recognize this as, using the mean value theorem again, be able to represent the distance as 1 plus the derivative squared at some xi star in the interval here. There's some xi star, not necessarily the middle. There's some xi star that we go and decide to use, and we plug that in, take the derivative, we take the derivative, square it, add 1, and then the delta x here is all from section 6.3. So if you don't understand this symbol here, just go take a look at the derivation for the arc length formula. This is a small piece of arc length here. It's not exactly the arc length. The exact arc length is going to be different from that, but we can approximate it by this polygonal arc length, this polygon, this straight line arc length. Okay, and this delta x, the change in x, is small enough what will happen is the difference between the function at the left endpoint and the function at xi star won't be too much different. We won't be able to tell the difference between them. We already know that y sub I minus 1 is this whole f of x sub I minus 1. But once again, if the change in x is so small, we won't be able to tell the difference between that and the f of xi star again. So pretty much the function at the left and the function at the right and the function at xi star someplace in the middle, they're all the same. And that will greatly simplify our formula. Okay, so we have a bunch of these that we like to add up, starting from A all the way ending at B. And so we're going to chop this interval from A to B into n subintervals and take the radius to be, so we have f of xi star twice here. So y sub I minus 1 is pretty much f of xi minus 1. And that's pretty much f of xi star. The other guy, y sub I, is f sub x sub I, f of x sub I, and that's pretty much f of xi star also. So we have two of these guys divided by 2, and so the 2's cancel and we just get f of xi star. So we have 2 pi f of xi star, and then this root of 1 plus the derivative of xi star, quantity squared, times this delta x. And that will be an approximation to the area, a surface area. And to get a more precise approximation, we're going to have to take more subintervals. So we'll take a limit as the number of subintervals goes to infinity. And it'll be a better approximation. This time it'll be exactly equals to. And this is a Riemann sum. So we get an integration. Now, what's so special about this is just one particular setup. There's many different versions of the formula, just like we had for shell. When we derived the formula for shell, there were many versions of the formula. And so for the surface area revolution formula, there'll be many versions of the formula, but this is one particular version where we have 2 pi times the f of x, 1 plus f prime of x quantity squared with underneath a root times dx. This part is ds. It's a part of arc length. And so this is the formula that will be true as long as you're setting it up this special kind of way that you have this function that is pretty much above the x-axis here in the first quadrant. It doesn't have to be, but we're revolving around the x-axis, and this is the formula that you would use in that case. So it'll be the area of the surface obtained by rotating the curve y equals f of x about the x-axis between A and B. Okay. Alright, great. Now, what about in general? What about if we want to rotate around the y-axis? So what about if our function is actually not a function of x, but a function of y? What if things are turned on their side? Well, what do we do then? So the next slide will be kind of cheat sheet ready material. It'll be able to help you make it through any problem. But remember the setup here. The reason why we derive the formula so that you can understand what's behind it, and therefore you can apply it to any kind of situation that you're in. We want to find the area of a band and then take infinitely many of them essentially. And the area of a band is going to be made up of 2 pi times the radius times the length. And now this length is going to be a piece of arc length. It's called ds. So the formula from arc length is now going to be a part of the formula for surface area. This whole taking the derivative and squaring it and adding 1 and having a root, that's now part of this formula as well. But there's more to it than just that. If it was just that, it'd be arc length, but now we have this extra part here, and it's all because we're taking and unrolling this band and getting the area of the band to be 2 pi r times h. Okay, so now let's look at a formula sheet kind of get you through any problem. If your function is continuous, and as long as you have a derivative that is continuous, then here's the situation. If we're going to revolve around the y-axis, this is not the situation that we had on the last slide that we derived, then generically this is your formula. Okay, when you revolve around the y-axis, where the y-axis is your axis of rotation, then your radius, so you got your function either y is f of x or x is g of y or something like that. Doesn't matter how the function comes at you, but your radius at that point then will be x. So this guy here is the radius, and this symbol here, ds, is essentially the height. This is the piece of arc length. This is ds is always going to be the square root of 1 plus your derivative squared, and then in this case dx. If it's in dy, then we just change it slightly. Okay, so when you revolve around the y-axis and you want to find the area of the surface, this is your generic formula, and then it depends on how things come at you. If you have the function given to you as a function of x, so we have y equals f of x. Okay, so then our integral then, if we like to do it in terms of x here, then the x from the radius stays as an x. And then the formula from arc length, the 1 plus y prime squared, that stays as the same, 1 plus y prime squared. Okay, so that is when you rotate a function f of x about the y-axis, that's the setup that you use. Now say things are for some strange reason turned on their side. If things are turned on their side, then we have, we can't put an x in here. Say we want to do things in terms of y. I have y between some c and d. So there's some two technicalities we have to deal with. The fact that x is the radius, when the integral is in terms of y, then we just we basically sort of invert everything and replace the x by g of y, the function. We'll see some examples of this. But then technically if we're going to do ds, then it's not 1 plus y prime squared. Technically it's like 1 plus x prime quantity squared. Okay, so revolving around the y-axis, it depends on whether you want to do it as a function of x or as a function of y. But generically the formula is always going to be 2 pi x ds, where x is the radius and ds is the height. So say you change things. Say instead of going around the y-axis, you want to go around the x-axis. Okay, so we have a function, it's continuous derivative, and we want to rotate around the x-axis now. The generic formula, like we had up here, is going to change now where your radius is no longer x, your radius is y. Sorry, not quite sure what's going on here. That's okay. Alright, so your radius is now y, and your ds once again is your height. Hold on one second here, I don't know what's going on here. What happened here? Let's try it again. Okay, seems like it's recovered, or maybe not. Okay. Okay, we'll just talk from here. So, sorry about this, 1 second. Okay, so your radius is y now when you go around the x-axis, and your height, your radius will now be the distance off of the x-axis. That'll be y, while before it was the distance off of the y-axis, which was x. This is your radius. Okay, so now it depends on how it comes at you. This is the formula that we derived. if you're going to do it with respect to x and your radius is y, this can't stay as a y. Just like here, we have to invert it and have it be the function of x that replaces it. ds is still the same. It's kind of like a formality here, the ds part. Just depends on which variable you're in. If for some reason you're in terms of y's, then the y is happy to stay as a y. The radius here, that's a y, is happy to stay as that. And so that'll stay as a y. So here it stays as an x, here it stays as a y, because you're in the right variable, but in the inverted cases, you're going to have to replace it with g of y or with f of x. Okay, all right, great.